right, so now let's go ahead and take a look at the field inspection of a centrifugal pump and motor. So one of the things that we're always doing when we go out and do inspections is, as we're walking up to the machine, we're taking a look at the condition of the base. We're taking a look at the lighting, the surroundings. We're looking for any leaks, anything obvious or untoward that might hamper the performance of the machine. So we'll take a look at the bolts on the base. We're looking for signs of corrosion. We're looking at the shimming. We're looking at the motor hold down bolts, the pump hold down bolts. We're looking for less than 4 shims. We're looking for warped washers. I take a look at the condition of the motor junction box. Take a look at the gasket there to make sure it's in good condition. Because as we just kind of walk around the machine, we're just noting in general the condition, looking above it, looking underneath it, looking at the belts, listening for any sounds, any rhythmic sounds, any squealing from the belts. Take a look at the taking a look at the supports here for the guard, making sure that the guard is in good serviceable condition, noting anything that needs to be written up to be repaired. Here we go. We're just doing a visual. There's a desiccant breather on top of the rotating element of the pump. We come in towards and look at the oil level and condition. Should be halfway on this bullseye, and the condition, it should be a clear amber liquid. We're looking a little oxidized potentially there. Here we've got a dripping of a mechanical seal, in which case that would tell you that that seal has failed. If it was packing, we should be seeing 6 to 12 drips per minute per inch of shaft diameter. But if it's a mechanical seal and it's dripping, it lets us know that that mechanical seal has failed. Taking a look here at the casing bolts, we want to see 2 threads sticking out from underneath the nut to ensure that we have full thread engagement and the correct clamping force, trying to avoid case distortion. We look at the suction piping, the discharge piping. Here you can see the eccentric reducer is fitted in correctly with the belly to the bottom. So, we're trying to ensure that it's not put in upside down and end up with a vapor being trapped in the top of the line that then slugs through. We want to see 3 to 5 pipe diameters of straight run coming out of the discharge. We're listening to the pump itself, whether there's any cavitation or gravelly rock sound, and deficiencies in the piping and a lot of extra elbows or not straight runs coming in and going out can give you turbulent flow going into the pump, leading to not a fully flooded impeller or fully flooded suction. And so, those are things that we're looking for. Now we get into actually putting our hand on the machine, feeling for heat and vibration. You should be able to hold our hand against that machine for 1 1,000, 2 1,000, 3 1,000. That would give us an idea, if I didn't have instruments, that we're probably at 140 Fahrenheit or below, okay, which would be ideal. And so now we'll take a look with at some of the local instruments. What are the condition of the gauges on the suction and the discharge? Actually, for a lot of places we go, we find the instruments, the pressure gauges, lacking on the pumps. So how do you know where it's running on the curve? Here we're taking a look at using a strobe light to verify the motor run speed. Should be very close to the motor nameplate speed. And if it's appreciably lower, gives us an idea that maybe that motor and that pump are overloaded. And if flow is proportional to load, that would let me think that we're asking that pump to flow more than it's designed to. Okay, and so just another bit of information. If you found that, oh, the motor's running hot, well, are we asking it to do more than it's designed for? And so, verify the nameplate speed and the run speed. We go ahead and grab the temperature gun, and we can go and check and identify whether the belts are running below 140 Fahrenheit or below. Again, cooler the better. It will help them last longer. You have a nice, if you look at the guarding here, you have a nice bit of expanded metal that's dark in color. Makes it easier to do a good inspection of the belts. Now we come around with the temperature gun and verify what we felt with our hands. Okay, by using the temperature gun, check the inboard bearing and the outboard bearing again, and document that temperature, those temperatures down, and look if there's been any change since the last time we did that. Now we can go, we can then go ahead and take a look at, there's our base. One more time, we've got our oil condition. And now we go ahead and grab the vibration pen, and we can check both the rotating element of the centrifugal pump for both velocity and acceleration. And so we do both a vertical, a horizontal, and then an axial reading for velocity and acceleration on both the inboard bearing and the outboard bearing. Okay, and so again, this would be something where you're looking at what are the failures you wish to control. You can go out there and do look, listen, and feel type inspections. You're going to have to do them quite frequently in order to not miss the onset of failure. With using a simple instrument like this, now you can probably do the inspections a little less frequently, but that's because they're documented. Okay, and so really in 5 to 7 minutes we can do quite a thorough inspection of the centrifugal pumping unit, and we can really identify a lot of potential items for improvement or for repair. And that's really the most important thing then, is taking what we found and now we have to act on them. Is it something the operator takes care of himself? Is it something he gets shift to do? Or does he write a work request in order to get the service completed?